when we talk about a crystal, I think everybody knows what that means. You say, yeah, that's a crystal. These are crystals. What makes it a crystal? Well, it's the order of the particles, or atoms or molecules. So in a crystalline solid, those atoms and molecules are arranged in a particular way, and it has a repeating pattern throughout the entire crystal. And as a result, we end up with these beautiful shapes. These crystals will grow with these shapes. You don't have to make them do that. Those aren't cut. They just grow that way naturally. Well, how can we figure out, or how did we figure out, how those atoms and molecules are organized? It was with a technique called X-Ray Crystallography. So we learned that electromagnetic waves can interfere with each other, causing interference. This happens with visible light, and it also happens with other types of electromagnetic radiation, including X-rays. So if we have constructive interference, then the waves add to each other, and what we saw in the box on the beach was a bright spot on the bottom of the box. And when they have destructive interference, then we have a dark spot. They cancel each other out. And so we see interference patterns produced by electromagnetic radiation passing through two slits or through a crystal. So, as was mentioned in that two-slit experiment, the distance between the slits has to be relatively similar to the wavelength of the electromagnetic radiation. So we can't use visible light to study atoms in crystals because their spacing is too close together. They're like 100 picometers from each other, so very close. But that corresponds to the wavelength of X-rays. And so we can take a beam of X-rays. This is a lead screen to filter out most of it, so we just get this one beam, and we shine it on this crystalline solid. And as it passes through that crystal structure, the atoms and the gaps between them act as slits and cause interference. So you get a diffraction pattern that's formed, and that reveals the spacing between the particles. And the diffracted X-rays might look something like that. And as you can see, it's not just a real simple matter to figure out that that would correspond to something like that. So how do they do this? If we have two waves that are in phase, they will have constructive interference if their wavelengths, the peaks line up on top of each other, right? So if these two rays are passing through different parts of the crystal, ray 2 is traveling farther than ray 1. When the extra distance that ray 2 is traveling is equal to a path length, the path length is equal to an integral number of wavelengths, then when they come out again, they will also be in phase, and you'll have constructive interference. If the distance traveled is not integral numbers of path lengths, then they'll be out of phase and they'll destructively interfere. So what they do is they change the angle at which the X-rays hit the substance, and they're going to adjust this angle until they get constructive interference here. And knowing that angle allows them to calculate the distances between the different atoms. And so there's all this math stuff here, right? It comes down to Bragg's law, which says that some integer number times the wavelength will be equal to 2 times d, which is the diameter of the atom, times the sine of theta, where theta is the angle of incidence. So this is all nice and everything, but I'm not going to test you on that. There might be some homework on it, though. It's just good to have an idea of how they did this. This is an early X-ray crystallograph showing the interference patterns. So they measure the angle that produces constructive interference, and from that they can find the distance. And this technique has been used to find structures of all kinds of things. Simple atomic lattices, proteins. And one of the most exciting things was this was used to find the double helix structure of DNA. And that was a huge discovery. X-ray crystallography was an important part of that. So this is just an example of a Bragg's law calculation. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So we want to use Bragg's law, which is this guy right down here. N lambda equals 2d sine theta. So they tell us what n is. This is the spacing, so that's d. And that's the wavelength. So those are the numbers that we're given, and they're asking us to find the angle. So the angle is theta. So I can rearrange this equation, divide this side by 2d, and divide the other side by 2d. And then I find out that the sine of theta is equal to n lambda over 2d. So I'm going to plug my numbers in here. N is 1, lambda is 154 picometers, 2 times 157 picometers. And the picometers are going to cancel out. So I've got 154 divided by 2 divided by 157. So the sine of theta is equal to 0.49044586 if you want to be precise. Sine is a function. You can't divide by a function. You can just do the opposite of the function. So the opposite of sine, the anti-sine, right, is, I'm blanking, inverse sine, right? Inverse sine, which is on your calculator sine to the minus 1. So this is sine of theta. So then theta is going to equal the inverse sine of that number. This is where it matters if your calculator is set for degrees or radians. So I've got that number, and I'm going to do inverse sine of it. And I'm going to get 29.4 degrees as the angle at which we got the maximum reflection, the best constructive interference. So it's basically geometry used to figure out the structure of crystals. Any questions?